Hello. We are going to start chapter 10. I counted the number of remaining classes, and I found that we only have 6 classes remaining, and we have chapter 10, 11, and 12. So I think I need to hurry a little bit. So please understand if you feel I'm in hurry, like we need to rush a little bit. So anyhow, from now on, I'm going to finish one chapter in 2 lectures. So that will be the rule from now on. So we are going to continue our discussion about hypothesis testing. In the earlier chapter, what we learned is how to carry out hypothesis testing. And in this chapter, we will consider some additional topics that follow the hypothesis testing. There are 2 main topics in this chapter. One is how to evaluate the accuracy of hypothesis testing. We have to think about error probability, how to evaluate the performance of testing. And the second topic we are going to consider in the next lecture is how to accommodate a null hypothesis with an inequality. In the previous chapter, we considered very simple hypothesis, but if the hypothesis involves some inequality, we have to consider a different method. So that will be the second part of this chapter. Let's start from the first one, how to evaluate the accuracy. Let's consider the criminal trial again, the criminal trial example again. So in a criminal trial, the null hypothesis is that the defendant is innocent. So it is the null hypothesis because if there is not enough evidence, the defendant is innocent. That should be the conclusion, right? And the alternative hypothesis is that the defendant is guilty. So only when there is a strong evidence of guiltiness, then you can judge that the defendant is guilty. So in this structure, we can think about 2 results, 2 decisions. One is the null hypothesis rejected. That means the jury or the judge judges that the defendant is guilty. So let's say the defendant goes to jail. And the other result is non-rejection. If the null hypothesis is not rejected, for whatever reason, just there may be no evidence, or there could have been some strong evidence that proves the defendant innocent. Anyhow, if the null hypothesis is not rejected, that means the defendant will be set free. So this is 2 possible results that realize in reality, right? However, no one knows the real actual truth, but we can imagine in theory, we can imagine what would happen, how it works out if the truth was something. So for example, we can think about 2 possible truths. So that is, the truth would be the defendant was actually innocent or actually guilty. It is never known in reality, but we are going to consider that to analyze the accuracy of testing, right? So the truth here is purely imaginary, hypothetical assumption, but we can think about them. So let's think about case by case. If the truth was that the defendant was innocent, actually the defendant was innocent. In this case, the 2 possible conclusions, either going to jail or being set free, one of them is wrong and the other is correct. That is, if the truth is innocence, then if the defendant was sent to jail, then that is an error. The decision is wrong. Wrong decision is made. If the defendant was set free, then the decision is correct. So like this, depending on the truth, you can see one of the results is an error. But the error changes when the truth changes. So if the truth is that the defendant was actually guilty, then sending him to jail is the correct decision. But setting him free is an error. So as you can see like this, depending on the truth, there are two types of errors. We are going to analyze these two errors independently, separately. So if we put the same rationale into the general framework for statistical hypothesis testing, you can say this. If the truth is that the null hypothesis was true, correct, then rejection is an error. We call this type 1 error or alpha error. So usually type 1 error is the term we use. So rejection is an error, but non-rejection is correct decision. Because the null was true, so you should not reject it. It is correct. On the other hand, if the null was wrong, then rejection becomes the correct decision. But non-rejection is another type of error, which we are going to call type 2 error. Type 2 error is when you do not reject wrong null hypothesis. Type 2 error sometimes are called beta error, but we are going to stick to type 2 error. By the way, I don't like these names. There is no reason why this is called 1 and this is 2. So I would prefer saying them like false negative, false positive, something like that. But they are names used by everyone, so have to follow them. So we will consider them in this way. So let's think about them in a graph. So suppose that a null hypothesis is that, so here is a line on a real line. You believe that the true mean, the population mean, is here at this point, mu 0. So you assume mu 0 is where the true mean is. And if given your hypothesis, and then you look at the data, and the sample average may have some random error, or can be different from the true mean due to the randomness. But if the sample average is it's very different from your hypothesis, then it is suspicious. I mean, your hypothesis becomes suspicious. You can feel that something is wrong as the sample average moves away from your hypothesis. If the sample average is far away from your hypothesis, then something is going wrong, right? So I say that as suspicious. It becomes more suspicious as the sample average occurs on this direction, in that direction. And so, using that intuition, we define rejection region based on that idea. We are going to reject the null hypothesis if sample average is away from your hypothesis. Far away from your hypothesis, then you have to reject the null hypothesis because something is wrong. So if the sample average is too much different from your hypothesis, then you have to reject the hypothesis, and we call that area as the rejection region, right? You learn them, and so these cutoff points are the critical values, and outside the critical values are rejection region, right? Lower critical value and upper critical value. We learned it in the previous chapter. And given the critical value, now you look at the data where the sample average is. and the sample average will be distributed like this if the null hypothesis is correct. I assume that the truth is that the null hypothesis is correct. Then x bar, the sample average will be, the sampling distribution will be centered around this point, mu. So mu 0 will be the center of your sampling distribution. So that means with a very high probability, the sample average will be close to mu 0. But there is some probability here and there on both tails. There are some probability that the sample average will be far away from your hypothesis. That's possible. So if that realizes, if a value that's quite different from the null hypothesis realizes, then you are going to reject the null hypothesis because you don't know the truth. Just observationally, the sample average is too small or too large, so you have to reject your null hypothesis, which can happen with this much probability or this much probability. So this is the rejection region. So the probability. So even if the truth is correct, even if the null hypothesis is correct, the distribution looks like this. So there is some probability that your outcome, your data, falls onto the rejection region. So you will reject the null hypothesis even if it is correct. This is type 1 error. Type 1 error probability is this shaded area, right? That is type 1 error. This is how we calculate the type 1 error probability. However, now we are going to consider the other truth when the null hypothesis is actually wrong. Now, distribution is shifted a little bit. So now the center is not mu 0, but it's another point. I would say it as mu 1. There is another point. Actually, the true mean is here, which is different from your null hypothesis. So your distribution is shifted a little bit toward mu 1. It is centered around mu 1. So distribution is like this. Then you are going to, so now the null hypothesis is wrong, as you can see here. So the correct decision is to reject the null hypothesis. The null hypothesis is wrong, so you have to reject it. But you are going to reject the null hypothesis only when the outcome, the sample average, falls on the rejection region, right? You can reject the null only when the sample average is on the rejection region. Otherwise, you cannot reject the null hypothesis. So as a result, rejection region is here and there. So other than those two areas, these in between them, in between the critical values is the acceptance region. So here, if the sample average is realized here, then you cannot reject the null hypothesis. So that will be a type 2 error because the null is wrong, but you cannot reject it. So it's type 2 error. That probability is this shaded area. So it is the probability that the sample average is realized on the acceptance region from the sampling distribution that is different from the null hypothesis. So using the sampling distribution that is not centered at mu 0, you can calculate the probability of the acceptance region. Then it will be a type 2 error, right? So this is a brief graphical introduction to what we are going to do. We are going to calculate the probability of type 1 errors and type 2 errors. And then you have to think like multidimensionally, like we are going to assume what is a truth And sometimes you have to pretend as if you know the truth, but other times you have to pretend as if you do not know the truth, but only the data. So both are mixed up. So please listen carefully and follow carefully. In the next video, I'm going to give you an example using this medicine. Okay, see you in the next video.